This is the Module 1 video on the competition between substitution and elimination reactions. I'll begin by reviewing some fundamentals of kinetics, because kinetic studies tell us about the transition state for the rate-determining step of the reaction, and therefore give us information on mechanism. Rates are measured by progress per unit time. So we're all familiar with the rate of travel. It is the change in distance over the change of time. And so we're familiar with miles per hour. Or if you live in a country outside of the United States, kilometers per hour. The rate of the reaction is similar. We can either measure the disappearance of reactants over time or the appearance of products over time. And in some cases, we'll do both, generally using spectroscopic methods to measure the decreasing concentration of reactant and increasing concentration of product. And so the unit will be concentration per unit of time. Most often, molarity per second, but for slower reactions, you will sometimes see molarity per minute. Rarely will you see molarity per hour. And then we describe the rate of the reaction as the product of a rate constant multiplied by the concentration of reactant or reactants, if there are multiple reactants. The rate constant does not depend on the concentration of the reactants, but it does depend on the temperature. For the data to be fully presented, the rate constant should be stated at a specific temperature. The experimental method for determining rate constants is a bit beyond the level of this class, although hopefully you will study that in an upper level class, perhaps a 300 level chemistry course. But in simple terms, this is an integrated rate equation where we measure the change of concentration over a change in time. This is for a first-order reaction for the disappearance of reactant over time. We also need to know the concentration at the beginning of the reaction. This then fits a y equal mx plus b equation, so we can graph concentration over time on the y-axis and time on the x-axis. The y-intercept is the concentration at time equals 0, and then the negative slope equals the rate constant. I show this last part just as an optional appendix, so that you know that it's not magical. Turning to the next page of the worksheet, to say a little bit more about rate constants and why they are important, we will discuss some reactions that can proceed by multiple reaction coordinates, each reaction coordinate giving a different product. Each reaction coordinate has its own rate constant. In a kinetically controlled process, which will be the case for many of the reactions we study in this course, the reaction with the fastest rate constant will win the competition over the reaction with the slower rate constant. If the rate constants are similar in magnitude, say there's only one order of magnitude difference between the rate constants, then you will see major product and minor product. Proceeding to the next page of the worksheet, this is now the heart of the worksheet. As you studied last semester, substitution and elimination reactions do compete with each other. You may not have studied this in detail, but I provide a historical quote that might be interesting in terms of the discovery of the elimination reaction. And so a few decades later, leaders in the area of chemical kinetics in the United Kingdom measured rate constants for salicylases of 3 tert-butyl halides, the chloride, the bromide, and the iodide, at 25 degrees Celsius. They measured the rate constant for disappearance of reactant, and then they divided the rate constant information into the substitution and the elimination components based on the yields of the alcohol and alkene products. Please notice that the sum of the substitution and elimination rate constants equal the rate constant for disappearance of reactant. The evidence is everything that is depicted here, including the identity of the products and the rate constants. In another paper in a series from this laboratory, for the secondary alkyl bromide, specifically 2-bromooctane, these workers determined the rate constants for unimolecular substitution and elimination in the first equation, and then upon adding aqueous sodium hydroxide, they determined rate constants for bimolecular substitution and elimination reactions, and obtained these rate constants as the evidence. Turning to the next page of the worksheet, this is our first claim, evidence, reasoning question. Based on the evidence on the previous page, I will direct you to make one of 4 claims for the mechanism of salicylases of 2-bromooctane in the presence of sodium hydroxide. Is the mechanism unimolecular? Is the mechanism bimolecular? Or is the mechanism on a continuum between uni and bimolecular kinetics? Or do you think that there is another mechanism that we should discuss? After stating the claim, I will ask you to specifically describe the evidence that supports your claim, and then to provide the reasoning linking your claim with the evidence. And then I'll open this up for discussion about the scientific principles to defend the claim. I'll scratch out the words evidence because we're really not defending that unless there's something wrong with the experiment. This concludes the Module 1 video on substitution versus elimination. The next video will deal with stereochemistry of elimination.